Hello, everyone. Welcome back to your uh, session of probability and statistics. What I want to start doing today, since we finished all the like probability distributions for whether they are discrete or continuous, we also looked at a linear combination of random variables. What I want to do today is to look at if I get samples. I know this is statistics, but in order to introduce it, we have to do some probability first. If I get a sample from a distribution and I find its mean, and let's say this distribution was the normal distribution, what would be the distribution of the mean? A little confusing, right? But we'll clarify everything. We call that the sampling because it comes from a sample. Sampling distribution of the mean, mu, okay? But we are going to find it for the sampling distribution of the mean of a sample. That's why we call that X bar, not mu. We'll discuss, the difference between sample and population when we start the statistics. But what I'm going to do is to tell you the following. Suppose I have a bin full of numbers coming from the normal distribution. And then I'm selecting a random sample, okay? A random sample. And I'm going to find the mean of that sample, write it down, and then take another random sample of the same size, find its mean, write the mean, and then draw a histogram of the means. It turns out that the histogram of the means looks similar to the histogram of the individual values. Meaning, if I draw the distribution of x, where x is the random variable itself, so I get a mean, right? Because that's what I'm saying it's coming from. But now I'm going to take samples from that distribution, calculate the means, and plot the distribution of the means. It's going to go something like that. Still normal, but you think that it's like shrank. We learn today why is that the case. You learn how to find the mean of a sample, right? So if you have a sample of size n and you want to calculate x bar for that sample, what do you do? And let's say n is 5, it doesn't matter. So you're going to say, you take the first one, so let's call it x1. x1 is not necessarily the smaller, the first one you pick, okay? Plus x2, plus x sub n, and then you divide by n, correct? So now if I tell you what is the mean of x bar, you tell me, oh, the mean of x bar, we call that the expected value of x bar. And since x bar is a function of x, I can write it as 1 over n times the expected value of x1 plus the expected value of x2 plus the expected value of x sub n. But the expected value of one number, if I tell you what is the expected value of x1, it means what is the expected value of the population from which x1 was coming. You say it's coming from this guy. And what is the mean of this guy? We called it mu. So that becomes 1 over n times mu plus mu. All of them are coming from the normal distribution, so the mean is mu. Meaning, how many mu's do I have? There are n. Well, simplifying n with n, you get the expected value of X bar is mu, meaning the mean of that distribution is also mu. That's interesting. Nice. I like that. But in order to draw the distribution, I also want the variance of X bar. Remember how we did a linear combination of random variables? Yeah, we took as if this quantity is squared, and then I took the square of this, and then the twice the cross product of x1 and x2, x1 and x3. However, if you listen to me carefully, I said I'm going to select a random sample from that distribution. A random sample meaning the individuals selected are independent. And what's the meaning of independent? Well, if I select one from the top, the next one I'm going to probably select it from the side and then one from the bottom. And so once I select one, what is the likelihood that a particular number would be selected? They are all equally likely. All equally likely. I'm not selecting like if I select this number, it doesn't mean that I'm going to select the one next to it next time and then the one after that or the one. No, I'm just randomly, I'm shuffling and picking a number or whatever, or ball or whatever. So the items I'm selecting or items coming from a production line, okay, I'm selecting them randomly. And because they are selected randomly, they are independent. And because they are independent, I simply going to get this, the variance of this plus the variance of that plus the variance of that, and there is no covariance. The covariance is zero. But remember what we did. We are squaring. So the 1 over n would become 1 over n squared times the variance of the first. Well, where does it come from? It comes from the normal distribution whose mean is mu and variance is sigma. So it's sigma square plus sigma square plus sigma square, meaning 1 over n square times n sigma square. N cancels with the square, and you get sigma square over n, meaning the standard deviation of x bar is sigma over n, over the square root of n. Take larger n's, and the standard deviation gets smaller and smaller and smaller. Let's see what does that mean in real life. Suppose that I was lucky enough to be selected as your teacher in math. So it's the first day of class, and I come and ask each one of you, what did you score? So I wanted to know how good you are in math. Okay, so I'm going to pick a student at random. I don't know you, so I pick a student at random and ask that student, he or she, and say, how well, what was your grade, final grade, or the score of your final exam last year? So they may say 65, they may say 92, they may say 71. So whatever they say, I'm going to select that as the average of the class. So if it says 64, I say, oh my God, I'm going to have hard time because the students are clearly not good in math. And they say, no, you're dumb. You picked one. What if you picked one who was not good at math or who was sick in the last 2 weeks or 3 weeks of school, so he didn't do well in the test, but he's a good student? How do you know? It's only one. You say, so what do you want me to do? Say, select more than one. So if it's a class of 25, maybe pick 10 of them randomly because you don't know them, right? So I select one sitting on the right, one on the left, one in the back, one in the front, one in the middle, boys, girls, the tall, short, white, black, so I try to randomize and use the average of these 10 students as a representative of the whole class. That definitely would be more accurate. I'm not saying it's 100% accurate, but it's more accurate than using just a single person. That's using a single person, that's using a sample. Sometimes you cannot, if it's a class of 25, I can look at the average in the books and I'm done. But if it's a production line and I have millions of items, and sometimes to check an item, I may destroy it. Like if I'm producing, say, steel bars and I want to know their tensile strength, I'm gonna make a tensile test until the bar breaks, and I measure what is the stress at which it broke. Can I check all my production? Sure, you can, but you will be bankrupt like before you know it. So you select samples. I'm not going to select one bar. No, because no two bars are identical. As I said, they are like your fingerprints. They look the same, they feel the same. You say, oh my God, they are the same. But what is the last time you got two light bulbs that burnt at the same second? Unless there was like a big problem with your wiring, but usually it doesn't happen, right? There are no two exactly alike. So we are finding the sampling distribution of the mean because the variability, which is a measure of error, is smaller and smaller. And that is very, very like critical to understand. So when we go to statistics, you understand what we do there. Okay, so now they have the same mean, great. And they have smaller variability, great. So how can I use that, in real life? I'm going to show you an example. First of all, because we didn't see how we usually you don't have like probability tables to calculate the probability. You used to do that during our days in the exams. They give us tables so we can measure, calculate. In fact, to calculate even sine and cosine, we didn't have calculators. So we had to read it from tables and it was a mess. But now we have calculators. So I have my calculator. It's a TI-84 Plus. I'm going to use it to solve two problems. I'm going to solve a problem on individual numbers, and then I'm going to solve another problem using samples to show you the difference. I'm not going to say to use the same problem, but two different problems. Okay, let's go and check the first one. So in the first problem, I say, suppose you have a distribution and it's a normal distribution. We are talking always here about normal distributions. Later, we will expand and see what if it's something else. In fact, what if it's a distribution I don't know of? I never knew it. We didn't learn it. Okay? Very interesting. You will see that. Example, I have mu for the normal distribution. So I have my x is normally distributed. We write it like that, normally distributed. So we write n. This is distributed, normally distributed, with a mean of 90. The first number is always the mean. The second number is the variance. And many people, especially I saw it in management textbooks, they use the standard deviation. But if they don't tell you, as an engineer, I would look at the second number as the variance and take its square root. So to reduce confusion, I'm going to write it as 4 square. Instead of saying 16, I'm going to write it 4 square. So if you are using sigma, you know this is sigma. If you are using sigma square, you're going to use the 16. Okay? So I'm not going to write mu equals 90. Okay, we can write mu equals 90, sigma equals 4. And I want to find three things. First of all, what is the probability that my random variable x, so if I select just one item from that distribution, whatever that item is numbers written in a paper and they are distributed normally, or elements in a production line, or a person grade or GPA last year out of a population of American students, say, taking the AP exam of whatever, calculus, whatever. Okay, so I'm just going to pick one element, and I want to see the probability that this element coming from a distribution that has a mean of 90 and a standard deviation of 4 is between 80 and maybe 92. Then I want you to find the probability that if I pick a number, it's greater than 95. And then number 3, I want to find the 90th percentile of the distribution. So we write it 90th percentile of the distribution. What does that mean? It means that I come in this distribution from negative infinity and calculate the area, and that is the percentile. So if the area is like 0.2, then this is the 20th percentile. What is it here? 50th percentile, because the right is the same as the left. It's like you are doing, I think you learned that when you drew the box and whisker plot or something. Anyway, so 10th, 20th, 30th, 40th, 50th, 60th, 70th. So I want the 90th. Did I say 90th or 95th? Oh, 90th. So where is it? So I want to draw a line here and say this is 0.9 and this is 0.1. How do I get that with a calculator? These are the 3 things we want. It turns out that in the calculator, what we are going to do here, let me bring it to your focus. I'm going to do second distribution. Do you see the distribution list here? And it shows me some distribution. You can draw some distributions, or show it, or you can find the normal PDF. I don't want the PDF. I want the CDF because I want to find the area between 80 and 92. So I go to number 2 or type 2 and then click. It asks me for what? So normal CDF. It asks for the lower limit, which is 80, the upper limit, which is 92, the mean, which is mu, and the standard deviation, which is sigma. It's that simple. So I'm going to enter 80, comma. We said 92, comma. 90, comma, 4. It wants sigma. And I get 0.685, which is the 68 or 68.5%, right? 0.685. Second, I want the norm, the cumulative also, but for values greater than 95. Greater meaning from 95 to infinity. How do I write that? Well, it turns out that what you need to do is to enter 95, and for infinity, you can write 1 E99. That's the highest you can get in the calculator. So you're going from 95 to infinity, comma, again, 90 and 4, comma 4. And that gives me 0.1056, roughly 11%. But that is telling you something. there is an area of 0.1056 to the right of 95, which is roughly the 90th percentile, right? It's 89.44 or something. So I expect the 90th percentile to be very close to 95. Do you understand what I'm saying? This guy has an area such that this is 0.1056. So this area is 0.8944. I want the 90th percentile. I want it zero point 0.1 and zero point 0.9. So it must be very close to 95. So maybe we change that. Let's make that um, a 95th percentile. So at least it makes sense. Okay. In this case, in this case, you have to use something called the inverse function. Okay? How do I get the inverse function? So you're going to go to the distribution again, but instead of taking 2, go to 3. Notice in 3, it tells you the inverse function, right? So what do you do here? You want to enter the percent, which is 0.9, the mean, which is 90, and the standard deviation, which is 4. And you got 95.12. Remember, I told you it has to be really, it would be, both of them would be, oh, I did 90, not 95. And that's why it got very close to 95. We got 95.1. That's my mistake. I said I'm going to enter the 95th, and then I read 90. So that was the 90th. So let's make that 95. And I get 96.58. Very simple, right? Now we can repeat that, but for a problem where I have a distribution, but instead of calculating these numbers for the distribution, I'm going to calculate it for the mean of a number, like of a sample size. So let's say what I have here is my x is also distributed normally. And let's take a mean of 110 and a standard deviation of 30. So I'm going to write it 30 squared. Because the normal distribution needs two parameters, the mean and the variance. But as I said, many people, just for simplicity, they write mean and standard deviation, which causes confusion to mathematicians who are very rigorous in, deciding what parameters they have. And let's say I'm going to take a sample of size 40. And then find the same thing. So I want to find, first of all, the probability that the x bar, not x bar coming from the distribution is between 107 and 112. Number 2, I want to find the probability that x bar is greater than 113. And maybe we did the previous one the same, like the first example. So let's take also the probability that the x bar is less than 108. And finally, since we did the 95th there, let's do a 90th percentile. So notice here, mu of x bar is the same as mu, but the sigma of x bar is sigma, which is 30, divided by the square root of n, which is square root of 40. So it gets very smaller. If that was 49, you get 1/7 of the original standard deviation. The error is reduced tremendously. Okay, so how do we do that? Of course, we are going to do it the same way, except that the standard deviation would be different. So if we come to the calculator, we did the second distribution, we go to number 2. We want to enter the lower limit 107, comma, upper limit is 112, comma, the mean is 110, comma, and the standard deviation is not 30, it's 30 divided by the square root of 40. Close the parentheses. And I get 0.4. This probability is 0.3999. So you can write it as 0.4. Now we can shade the normal distribution. I think you should enter the same thing. So if I say 107, comma, I never used it, I think, or maybe in the past, I can't remember. I didn't use this specific calculator. I think it's the same thing. So I will enter the same numbers and see if we get the same result. So here is oh, no, that's not the shaded. What did it do? It gave me the area as 0.399 lower and upper, but I didn't expect it to. I thought it will show me so this is the mean. No, that's not the mean. So I don't know what that is. It's just, I'm sorry. I should have tried it before. Anyway, let's go to number 2. So number 2, let's say this is part A and this is part B. Maybe you would explain to me in the comments and how to use it. I don't need to shade it anyway. Second one, I want the probability that X bar is greater than 113. So we do it the same way we did that. Okay? So we say the lower limit is 113, the upper limit is 1E99, comma, 110, comma, 30 over square root of 40. And that is 0.2635. Roughly 26% of the distribution of the means is greater than 113. Notice that only 10% for this guy, 10% was greater than 95 when the mean was 90. So it was like roughly 1.25 standard deviation more. But now the standard deviation is no longer 30, or else this number really would have been very small, but now we have 2635. What about B? How do I enter that? To enter that, oops, I wanted to go down one and I clicked the wrong button. I wanted to go down first. So here you would say I am going from negative infinity up to 108. The mean is 110. So I am below the mean, so it's definitely less than 50%. And the standard deviation is 30 over the square root of 40. That gives me 0.337. And finally, to find the 90th percentile, you do something very similar. So you say second distribution and you go to the inverse norm. It asks you for a percentage, so you say 0.9. It asks for a mean, you enter 110. It asks for a standard deviation, it's 30 over the square root of 40 as usual. But you enter only 3 things, not 4, because just the percentage. There is no lower limit and upper limit because you are not finding probability. And you get 116.07. That number in the distribution that has a mean of 110 and a standard deviation, if we say the square root of 40 is roughly 6.5. 6.5 is 42.25, so like 6.4 or something. So 116, 6, and 6 and 4. So it's far away, and that's why this percentage is only 0.1 and this is 0.9. You go the top 10%. Okay, I hope this was easy. I wanted you to learn how to find the sampling distribution of the mean. We are going to talk what if that distribution wasn't normal next time, and then probably we'll start developing what we call confidence intervals. And maybe after that, we do some tests of hypotheses for the mean and maybe for the variance. We'll see. We'll see how it goes and what we cover in this course. Okay, thanks for your time. Hope to see you soon. Have a great day.